Hey guys, welcome to the Cell Doctor channel. I'm working now on analyzing the power distribution on the PCB for the Megacell Charger Professional. I finished fixing the main input, which will be 12 volts power supply. I managed to get it from 200 amps per millimeter square to 56 amps. This is showing the regions where the amps get high, where like I can locate the region where it shows like the peak amperage right here. So that will be not a big deal because it will generate heat and dissipate into the board when this happens. But now I want to solve the issue, or actually let me see if I can make this plain. Let's see if it changes anything if I round that edge instead of having it straight like that. So yeah, let's try that. How do I make it? Polygon. Not very round, but I don't seem to have any tool that does that. Fine, circle fill. Arc edge. So I will try with this to see if this changes. Okay. But I want to get the ground fixed now. So this is what I had before. Like it was picking at 219 amps in some regions. The thing is that the original PCB had only 2 layers and it was running fine at 16 amps, and now we upped the voltage to 12 volts. So that will drop the amperage, but we also change the charging IC, which is charging with about 20 watts maximum. So if we provide 12 volts to the charging IC, it will eat about 1.6 1.7 amps when fully charging. So if the old board worked fine, we did not had any burn traces when fully charging, upping the voltage to 12 volts should ensure that we're still the PCB is still going to function, but this is for me, for my peace of mind, because I have solved some of the issues when some traces were going through the power plane and it was cutting that out. So I switched those traces to different layers, and I also added more copper to one of the inside layers that will also drive the 5 volts. And this should be more than enough. It's nothing beats the physical test, but if you have a tool available to help you test this thing, why not? Why not use it? Right, so let's run the analysis again. Let's pour all the polygons. By the way, I finished arranging all the new ICs and connecting everything in place. Now I'm doing the final inspection, fiddling with the power planes, and also I also added more VS for heat transfer here at the top, and I added some pads here as well. Let's have a look at the 3D view. Which for some reason is not displaying properly. Let me move this around. The PDM tool switched some things off, and I'm not sure what it did. Let's see if I can reset this. Or use. Jumpers. Yeah, anyway, I'll look it up later. So what I wanted to show you is that I added some pads on the back. I can show it in 2D as well. So you have some pads here where you can play some heat sinks, where we can play some heat sinks in case the board gets too hot, but I don't think it will be the case. And I also play some pads on the back that will allow us to connect an accessory to discharge the cell with higher amps, 5 amps or more. Maybe we can have our own accessory that dissipates heat on a radiator or something like that, and that will improve the the heat dissipation when you're testing larger cells. We also want to make with that accessory the ability to charge other cells, so that will be a plus for some of the users that are testing large cells and don't want to waste the electricity. So I will start the PDM analyzer now. I have already declared the main components that are the big QICs and put it at 1.7 amps. Here it shows the 5 volts because net names remain the same. The old version was 5 volts, but now it's from 5 to 16 volts the input. But I put the input voltage set to 12 volts to calculate the current that it's needed by the current that will be carried by the traces on the PCB. So it takes some time to perform this analyzing thing. Takes about 5 minutes. And meanwhile, if you're still watching this and you did not subscribe to the channel, please do that so you don't waste your time just waiting. Click that subscription button and you'll be notified when I'm going live or when I post a new video. I'm planning to add a lot of new updates on about the Megacell charger, improve the documentation as well, add all the features I discussed in the previous videos for constant current charging, constant voltage, and also constant resistance for discharging. And also we'll be able to communicate with each IC independently. I look forward to test all these new features, see them implemented, and see how the charger will behave when fully loading it. What is the maximum current draw that we can have for running all the cells at the same time, charging at 3 or 4 amps. Oh, sorry. That should provide some nice heating patterns watching with the thermal camera. Should see all the all the power being distributed to the charging IC, similar to what we see in this analyzing tool. That will be on the physical thing, and I think everything will be fine as long as we keep the voltage more than 10 volts, 10, 12, even 14 volts. That will lower the current that is driven through the PCB. For 5 volts, we should be specifying that the maximum will be about 20 to 25 amps. So you should, let me pull a calculator. So we should have about 25 amps divided by 16. The charging should be set at about 1.5, 1.6 amps maximum if your input voltage is 5 volts. Otherwise, you risk running the PCB when you're running. If you have a, let's say, 80 amps, 5 volts power supply, that's 400 watts. When you supply all that power to the PCB, it's going to produce a lot of heat because it's running the current at lower voltage. So the power needs to get there. It will get in current mode, not through voltage. So that most probably the new version will be coming with 12 volts power supply. So for 12 volts power supply, we'll need about 30 amps. That will be top. So 27.27 amps. So we have 16 multiplied by, let's say, 1.7 maximum current draw. So yeah, it's 27 amps. So 30 amp power supply, 12 volt power supply. That'll be around 360 watts. That should be your regular PSU from a PC, from an old PC that you have. Those are mostly rated at 400 watts, so that should work pretty well without needing to buy a new power supply. Most probably any DIYer will have a bad computer power supply. A power supply from a bad computer. That's what I wanted to say. So, because the power supply needs to work in order to use it. Okay, so this is still going. Complete 0 of 1. Let's look over this picture and discuss about what has changed. I think I had a more detailed one. Yeah, this one. So you see in the previous example, I'm actually save this so we can zoom in. Okay, so you can see that I had these traces going through the power planes, and that was cutting this plane and making very small regions, couple regions where the current was going through. So I moved these traces from the second layer to the third layer. Right now I have the first layer, which is the top layer, being power for 12 volts, and also the second layer. It was this is the second layer we're looking at. This one was chopped off by these traces, and at least here, because here we have the input, here it goes the power, and from this point it's going to both sides. And I checked, and we should have a 0.1 voltage drop from this point to the most farthest point on the PCB. So that's fine, because the BQ ICs can handle voltage anywhere from 5 to 6 to 17 volts, 4.5 to 17 volts actually. So a 0.1 voltage drop is not going to count. But we need to make sure that we are not overheating the PCB. During charging, we should not have this problem, but if some of the cells charge, it should balance out, because if some of the cells are charging and some of them are discharging, the power dissipated by the cells that are discharging is compensating the charging power. So it should be a balanced setup, so we don't have any issues with that. So this one actually finished, and here you can see it shows the voltage, and let me set it on the side here so we can look at the PCB. I will have to switch between screens to show you what I'm doing. So you can see that we have this chart right here that's showing us 12 volts. That's what we input in here, and the maximum is 11.9. The minimum voltage that goes is 11.9. So here is the maximum. No big deal here. And let's watch the current density, because that's what we're interested in. Alright, let's watch that chart. So it's 56.9 amps, almost 57 amps per square millimeter in some regions. Of course, this is not going to simulate 100% what happens in reality, because the way this interacts with the other layers and the way it dissipates the heat and the way it interacts with the vias, because here we have vias here where you see these spots. There are vias that are conducting the let me switch. Yeah, let me turn off the other layers, see if it's more clear. So this is the top layer, and from the top layer the power goes to the bottom layer as well. We also have vias here at the connectors, so each layer is interconnected. On the big connector right here that we have the screw connector, so power is being distributed. And here we have this kind of, we can actually probe and here we have 50 amps, but you can see that on this kind of trace we have 24 amps per square millimeter. So these are the zones that may produce some heat. And right here we have 1.3 amps going through the IC. Okay, so let me check the power plane, see if there's something to fix there. Okay, so this kind of region may be problematic. Which layer is this? Layer 2. Here. And you can see that these arrows are actually showing how the current is going, so it's pretty cool. You see the direction that the current flows. Yeah, sorry guys, I have to take this. Sorry about that. Okay, so let me take some notes. I will open Photoshop. Okay. Here we could be adding some vias on these regions, or nothing consumes from it actually. There should be vias. Let's see. 5 amps. So one top layer. The reason I'm doing this is that I want to make sure that the board will not go up in smoke when we are charging, fully charging the using the new ICs. So this gets to 40 amps per millimeter, and it's in this region right here. Okay, so also top. Oh. I'm switching layers now, and when it's switching layers, it takes 1 or 2 minutes. I probably need a new computer to run these simulations faster, but right now I don't plan to get a new computer. So we see on layer 2 that we have some steep areas. Okay, so these areas here I want to remove. I will drive the copper lower so it totally cuts this, so current flows in a different direction to avoid having such spikes. Okay, so on layer 2, have here? Here we have 37, 39 amps. Okay, so these two spots up and here. What I want to check. Let's close this. Okay, so what we can do is to increase that area, move these vias around to allow the current to flow. And I can actually move this line even more. What the hell? See if we can. This is for the length matching. So we have the same impedance on the traces. And this is the shortest trace because it's going directly from the IC to cell number 9. It needs to, okay, so when it's green, it means that it matched the length with the others. Having this messy spaghetti here allowed us to get the 4 digits precision when measuring. Let's see if when measuring the current and also the voltage. Okay, so this one should be solved. The main issue with PCB design is that it eats a lot of time. You can find yourself moving these parts around and look at the clock, and 3 or 4 hours passed without even realizing. So it eats time like nothing else. This and 3D modeling. When I was doing 3D modeling, I could find myself do that for an entire day, and when I go home, I feel like I'm floating. My legs start denumbing. Alright, so this one got a little funky here. I don't want that. Okay, so that area was solved. Now I have to show the polygons. Okay, so this should offer a wide enough trace for the current to flow. And there was another one here on layer 1. Here and here. Yeah, this one. Place a via right here. This is for the temperature sensor. I also spread apart the temperature sensor, the one that we use for reading the temperature on software, and the one that the IC uses to determine if the temperature is fine for keep charging it. This should stabilize the cell a bit, because when I had just one temp sensor, some users claim that the cell is rocking, and that was true. But if you pressed it at the bottom, the cell will stabilize, like make proper contact. But I hope now that if I'm placing them apart and you have 2 points to rest the cell on, it should not be rocking. Otherwise, I will have to find a different way to stabilize the cell so it stays a bit better in place there. I thought to try some epoxy, but I will see what I can do. Okay, so I moved this part. Let's see if there's any other things that I should improve here. Yeah, I think this should get rid of the hot spots for current on this layer. Let's repour and analyze again. I also don't like this area here. Let's see if I can move this. I want to move. Okay. This new WhatsApp is annoying because it doesn't want to turn off from the desktop. Before there was an icon where I could turn it off, but now it seems to send the notification no matter what. I should find it in Task Manager. Okay. So let's run the analyzer again, see if we can keep it under 40 amps. Now you see, I closed it. Mute shut. Yeah, that should do it. PDM analyzer. This is probably a boring video, but sometimes work is not all about the excitement of releasing something new. Okay, it's out there, it's working, and no, you have to wait for the software to do its thing, to wait for the manufacturer to do its thing, to find the components, find the best prices, otherwise you cannot actually afford producing the units. Fix some issues. We had some issue with INA 219 IC, that's for current measurement. And we found a supplier which offered us a better price, like 50% less than what we had on a different supplier. And we thought, okay, it's an IC. We tested a small sample of 10 ICs. It worked fine. We actually tested one IC from that small sample of 10 ICs. But it worked fine, so we thought, okay, it's the same IC, why not? And then when we produced the units, we had like 20% of the devices not working, and we thought, okay, what the issue is. When we got the devices, we discovered that some of the ICs, the current reading ICs, were busted, were not working, and we don't know if they were malfunctioning before installing or if they got malfunctioning after installing. But I think they were bad from the beginning, because all of them received the same temperature, same type of soldering. So we had to rework all those ICs, desolder them. It's a small IC on the back, it's not a big deal, but you still have to rework it, clean it up, test the board again, see if it works fine. So sometimes when you're trying to find the best deal, you might encounter some issues like this, because they probably had a bad batch and they were mixed. The ICs were mixed with some good ones, and they didn't want to spend the time to find which ones were good and which one were not, and sold the whole batch at a smaller price. And we paid the difference in reworking those PCBs. But you live, you learn, and try to avoid some of the mistakes and make others during the process. But I think the most important part is to learn how to solve those mistakes that you're doing. Otherwise, you do one or two mistakes and say, okay, I'm out of this. I'm no longer doing this. It's complicated. It's prone to error, to human error. But everything is prone to human error. Okay, so this is still going. I have more than 2 months now working on this PCB, and I thought it will be a quick update from 2 layers to 4 layers, and I ended up changing most of it, but it's a good improvement, and things have to evolve. If I would have kept the same ICs, none of the new features will be available. Yeah. Still going. Simulation progress 99.8%. Give me the extra. Oh, simulation 100%. Load and analyze results for unnamed simulation 1. Yeah. I'm running an unnamed simulation. Should be called my simulation. That's what we were doing at first when learning software. You will create a project, call it my project. All right, your project. And after a while, when you wanted to find your project or which project you wanted to work on, you will say, my project. Which project? Mine. So let me get this plate. Okay, so voltage drop remain the same. Let's see the current. So at the top we have 56.9. Let's check it for ground. I'll have to run a test on the PCB after I receive it to see how it compares with the simulation results, so I know for the future when I'm seeing that I have some high numbers like 56 amps in some regions, see how that translates to the actual PCB. So I'll put the thermal camera on, load the cells in, set the maximum charge, and then I will get the readings of the PCB. One thing we can do is to change from one Oz, to change the copper thickness from 1 Oz to 2 Oz. I don't know how that's called in ounce. Ounce, yeah, it's an ounce. We're speaking in millimeters here. Ounces are not used. It's like, so we can double the thickness of the PCB and also for the inside layers, and that will easily take more heat and more amps going through it, but that will also increase the cost of production, because 2 ounce thickness, it's not used in all the general production PCB, so they have to create a special batch for you, and also there's more copper depositing, and copper is expensive. The PCB thickness will also get a bit thicker, from 1.6 millimeter to about 2 millimeter. That's not a big issue. We have enough room in the case for the extra 0.4 millimeters. But that's why we test. That's why we test, and that's why we create prototypes. That's why we can actually specify in the software not to charge for more than 3 amps if you don't have the proper voltage at the input. If we are measuring a voltage of 5 volts, I can actually set the IC, the BQ IC, to have the voltage, the required input voltage set to 11 volts. And this way you can use the 4.5 amp charging, full charging. If we detect lower voltage, you can still use the charger, but we'll cap the charging current. the 2 amps or 1.5 amps. So we have the tools or the way to do it. There was still one more spot that I forgot to touch up. These ones here. So. Okay. Okay, I managed to find what was the issue. So now I actually changed to black, the way that our PCB works for Megacell Professional, Megacell Charger Professional version 2.0. Function button. So I was saying that I added these pads right here, these ones. We could place some small heat sinks there, solder them in place, or we can use them to connect the wires. It will be plus, minus, plus, minus, plus, minus, to connect the wires for external charger or external discharger. Okay, I'm going to run the analyzer one more time, and I will leave it as is for now. But first, let's run the DRC. I'll make sure. I think there are some things that changed. Let's see the match length. Yeah. So which ones? These ones here. When moving traces around, sometimes you make them longer and you need to readjust them. Okay. And that's why I said you can spend hours and wondering what happened with your time and with your life. And then you have people complaining, oh man, this doesn't work right. True, need to put more time in it. I'm not saying that this has been a perfect project, because it's hard to make something that's perfect from the beginning. You need to put the hours in, find the issues, have people that properly report those issues, because for me it doesn't say too much when someone is saying the device is glitchy. Okay, be more specific, please. Why is glitching? What type of power supply you're using? But hopefully, from the professional version, we don't have this power supply issue anymore, because I guess this is more than half of the time the tickets we got so far. And the issues with the chargers was the power supply, because we offer the option to get the device without having to pay for a power supply. So you use your own or get it from the area where you're at. There is still some clearance constraint. Clearance. Okay, I also have a short circuit. Nice. I don't want short circuits in my design. There is another one here. But did this move around? Yeah. Yeah, I think it moved around when I moved some of the traces, but it should be fine now. It should be locked. Yeah, now it should not move around. Okay. Okay. No rule violations. reanalyze. Another 15 minutes of waiting. This week I should receive, I think this week or early next one, I should receive the 4.5 amp version from the JLC PCB. I think I said it earlier as well. But I'm sure no one is going to notice it, because this ended up being a very long video, so not too many will watch it start beginning to end and complain that I said things twice. If there is anyone that saw that, I'm curious, who would that be? And why would you watch such a long video about designing a PCB? Because you might not care too much about how this is designed, but you just want it to work for you. But I said, why not showing the process of designing this, keep people updated. Maybe some of the do-it-yourselfers want to get into producing their own PCBs as well. Now that I'm thinking, maybe we'll make the old version open source as PCB as well, so people could produce their own if they want to. They want to get into making their own PCBs, making their own version of Megacell chargers. So if you are interested into that, let me know and I will think about it, talk with my colleagues as well, see what they're thinking. Because I don't see any reason not to release the files for the old PCB, because I think that we will stop producing it. There's no reason for us to keep producing the old version with the TP4056. There is a small price difference, but in the number of features and the quality of usage, like 15 to 20 bucks difference in parts that we will pay to get the professional one. Because I optimized the parts, I'm no longer using the four PCFs on the back. So right now we're paying extra for the BQ IC. That's the most important part for charging, because before it was a few cents to buy a TP4056, because that's very popular charging IC. It's used in those charging modules, and it's not doing too much. It's not communicating via any way I2C or whatever other communication algorithms or ways are there. So it's just setting the current through a resistor. So you place a resistor there, and that's setting the current. If you want to change the current, you have to change that resistor. So those are very popular and not very complex ICs, and they are built in large quantities, because a lot of those TP4056 can be found in the small devices that require charging. So the BQ one is more advanced and not that popular that you will get it as cheap as the other ICs, because this is the main aspect on pricing these ICs, because it's not more material to add there, it's the technicality of building that IC, and also the time it was put into designing the IC, and also the value you get from that IC as a user. So that's how you price things usually. So yeah, we might consider releasing the Cell Doctor 0.93 version. As an open source. I think this is going to be a cool project for some users. I would not prefer building my own if I don't have any experience with components, finding parts, soldering them, because on prototyping websites, some components you won't be able to find, especially those heatsinks here. You won't be able to find them very easy. Those are custom made. But I will tell you how to get some in case we release this. We might be able to offer you some as well. We might give this as a kit. If there's more than 10 requests, I will say, I will do it. I will probably make another video and talk just about this thing. But first I want to finish the professional version, the professional Megacell charger, and then I might consider doing other things. I want to do a lot of things. It's not that I can do a lot of things related to the software of the Megacell charger, to building a library for Python. There's a lot of things, there are a lot of ways to spend time working on this project, but because I have limited time and resources, I need to find the things that are most important and are offer the most value to the customers, so I can actually keep this project alive and keep going, keep producing new units, and keep upgrading the software and the hardware as well. Alright, so I managed to talk my way through another analyzing. It's loading the results now for the simulation. Alright. Let's sorry about that. I ordered some parts from TME. I got a cell, a high discharge cell like this one, so I can test different charging rates and so on. And they sent me a nice t-shirt. I don't have it around because I wear it yesterday, and that got me an idea of getting some designs about batteries and stuff like this, because I have a friend that's producing what? This is another layer, I guess. I have a friend that's producing t-shirts, and we'll try to see some designs. Maybe there'll be something interesting to add on the shop as well. At least send it with larger orders. Send a t-shirt. So let me turn off the layers. No, this is the 12-volt input. So 40 amps here, good. 56, 34. Okay. Let's put some music that will not make YouTube complain. Oh, SoundCloud. I was listening radio yesterday when I made the video, and then I got some notification that I got some copyright. Got copyright reported. Can still keep the video, but I don't like getting complaints. Okay, so for the top layer we have 42 amps per millimeter square. $37, so that's okay. 56. Where is the spot? Here in this area. Yeah, I think that this is where I stop on working on this. I will do the physical test to see if we have any issues charging, and then I will compare it with the data I get. I'm going to generate a full report. Save this one. That's pretty cool to see that on the input we get 1.7 amps, but the grounds gets only half an amp draw. That's cool to see where, because Q4 it's providing ground to the IC, so only half an amp goes through there. I think because the electricity goes, the flows from positive to negative. Yeah, flows in that direction, from positive to negative. Plus to minus, minus to plus. It goes from minus to plus. It goes from negative to positive, actually. All right. Pen current. This is the small load. All right, so this is the report. I'm going to end this video here. If you looked through this video and skipped through the end, basically what I did in this video is trying to optimize the power distribution on all 4 layers for the Megacell Charger Professional version which is on 4-layer PCB, optimized with new ICs for discharging and for charging as well. I finished the design. I have all the new features in, and now I'm going to generate the production files. I'm going to run DRC once again, save a copy of the source to an external drive in case my computer fails somehow, and then I'm going to send the files to the factory, send the BOM bill of material, check for all the parts that are correct in the bill of material again, and then we are going to produce a physical version of this PCB with all the parts assembled, put it to the test. I will stress test it for 1 or 2 days, and then I will give my okay if everything is fine to the factory to proceed to produce the rest of the PCBs. Right now I'm going to produce the prototype directly at the factory. This will ensure that we have the design checked, the actual design checked at the actual factory that is going to produce the PCB. It should be no difference, but there can be difference in the parts that are sourced from different suppliers, so we want to check that everything works fine before launching a larger order. And after that we will move forward with the software, produce the software required to run this new device, and we'll see what happens, if people will enjoy working with it. We have reached 30 pre-orders, which is the minimum that I could produce this on a factory. I will actually get 2 or 3 for myself as well to keep here in the shop to test that everything works fine, and send one to Martin and one to Mihai, my colleague, as well, to play with them, burn them if they have to check their limits. I burned 2 as well so far to check their limits, and I found out that I cannot combine some things how I wanted, but I still found ways to use it the way I want to charge new cells and stuff like this. But this is coming in later videos. I need the project to, I need the software to work first, and then I will play with other things and make more videos about this charger. Thank you very much for watching, guys. Thank you for supporting this, and I hope you can start supporting this channel by sharing this project. You don't have to share this video because this video was a lengthy one and not very to the topic of batteries. It's more for PCB design and stuff like this, but I'm sure you can share other videos from the channel related to the Megacell charger or to the battery repair I just did a few days ago. Find something to share, please, because I want to grow this channel to at least 1,000 subs, and then move on with creating more projects for this channel for batteries and also related to the Megacell charger. It's something I want to be doing for the next years as well, so that's why I want to focus on this, get things ready, get things working properly, and help people make something that it's useful for people, speed their process for testing cells, work on getting some knowledge material done for building batteries, and finding cheap ways to build that. So again, guys, thank you very much for the support. Don't forget to subscribe if you're not already a subscriber, and to like this video if you find anything that useful or just for the support. Have a great day. Alex.